force F is equal to alpha I plus 3j plus 6k is acting at a point R is equal to 2i minus 6j minus 12k. The value of the value of F, which okay, so the value of F which for which the or at which angular momentum about the origin is conserved is okay. So see, before we go much into the solution, well, see, if you were to ask for the simple solution, it will go like this. What is torque is equal to? So we have 2 is equal to vector r dot r cross F, and this is equal to 0. So all what you need to do here is find out this determinant ijk. What is r? R is 2 minus 6 minus 12, and what is F? F is alpha 3 6. Equate this to 0 and you will get the value as alpha. Simple. But that's not the point here. Since we are trying to understand the concept behind every question, um, what we should do in detail is to understand the logic behind every term which is given to us here. So we'll start with at a point, okay. Force is acting at a point, so there's not much detail given at a point. The value of F's angular momentum is about origin. Okay. So what I would like to do is I would like you to understand the basics of momentum here. Okay. So let's first write it down. So when we say the term momentum, we should be more specific about what kind of momentum are we, mentioning about. So momentum, it can either mean linear momentum or it can mean angular momentum, depending upon the context. Now, when it comes to angular momentum, we again have two types. Let's say two, not two types, would be two scenarios where an angular momentum could be defined. One in which the object considers a point object, okay, is a point object or regular figure to be more precise, and the other one angular momentum of a rigid body, or maybe an irregular body, or let us use a what other word would be irregular, or maybe an extended object. That would be more correct. Okay, of an extended object. So point object or a regular object. A regular wouldn't be a more precise here. Point object or a rigid body or an extended object. Okay. Now let us see the difference between angular momentum here. So when we say linear momentum, okay, let us first understand the different cases properly, then we'll be able to figure out well. So if we were to discuss about linear momentum, what is this? What is the picture that would come to our mind? See, there's an object of mass m. Okay, it is moving with velocity v, and in this case, the linear momentum is nothing but the product of mass into velocity, which is mv. Okay. Now let us see the case of angular momentum. Angular momentum. So the scenario here is there is a ball of mass m, right? There is a ball of mass m. Okay, there is a ball of mass m, and what's happening to this ball? This ball is executing. It is executing a rotational motion. It is executing a rotational motion. Okay, passing through an axis, at a distance r, passing through an axis at a distance r. So let us try to visualize that. And how would we do that? Say, so there's a ball here. This is mass m, okay, and this is the axis, okay. Say, okay, let's a ball of mass, let us say it is tied to a string. Yeah, now it will make more clarity here. So this is the string here, right? And this is the mass. This is the ball of mass m, okay. And what's happening to this? It is again moving with the, it is given a velocity like this, right? And what will it do? It will execute a it will execute a circular motion. It will execute a circular path like this. It will execute a circular path like this. Right. So this is execute a circular path like this. In this case, what is angular momentum? In this case, angular momentum is defined as L. Angular momentum is defined as L, which is equal to linear momentum P into the distance, into this distance, which we'll write it as R. Okay, so we have linear momentum into R, and therefore L is equal to mv into R. Right. So this is linear momentum. Also, this is angular momentum for a point object. Now what we need to understand further is angular momentum of an irregular object, something really important. So let's try to understand the derivation of this. So we have angular momentum of an extended object, of an extended object. So let's try to understand the concept behind this. So here what I'll do is, we have a reference axis here, right? And earlier we had a string which was attached to a ball. Instead of that string and the ball here, what we have is a rod. A complete rod is kept here. So we have a complete rod of mass m, of course of length r, and the same parameters apply here. This entire rod is moving with velocity v. Okay, so we're not going to discuss this part now. We just have the comparison here. So how will we understand the angular momentum here? Let's see the concept here. So understand the angular momentum, what we are going to do is we're going to split this mass or a rod of mass m into different smaller masses. So say I divide this into m1, m2, m3, m4, and etc. up to mn. Okay, and then I'll consider individual masses and try to find out the angular momentum and then add it up. Okay, so why am I doing this? What I'm trying to do here is I'm trying to find the angular momentum of the rod, which I'll find it as angular momentum of mass m1 plus angular momentum of mass L2 plus angular momentum of mass m3, etc. up to angular momentum of mass n. This is what I'm trying to do. Okay, so instead of finding the angular momentum of the complete rod, what I'm going to do is I'm going to compare. So I'm going to find out the individual angular momentum of these blocks and then add, so that this gives the complete rod. Okay, so that's logic behind this. Now, how do we find the angular momentum of this mass m1? This mass m1. Let's see. See this v. When we say that the rod is given a linear velocity v here, it doesn't mean that this m1 will also receive v. Why? Because m1 is not at r. m1 is actually at a distance r1, which means there would definitely be a change in velocity, right? And here the angular velocity experience would be different. Okay, the angular velocity experience would be different. I'm sorry, the linear velocity experience would be different, whereas the angular velocity would remain the same. Now, what would be the linear velocity experienced here? See, that would be equal to v1, which by the formula we know that what is v is equal to r omega. So here v1 would be equal to r1 into omega, right? So we have v1 is equal to r1 into omega. Now let us write down here. So what is L1 or moment of inertia? Sorry, not moment of inertia. What is angular momentum of m1? That will be equal to p into, right? That will be equal to p into r1, right? So what is p? P is m into v1 into r1, right? So we have m into v1 into r1. Now, let us understand the next mass, which is m2 here. Now, m2 is at a distance of r2. Okay, understood. M2 is at a distance of r2. Now, this again will be experiencing an angular velocity omega. Now, v2 here would be equal to r2 into omega, right? Because it's a different mass and it's a different velocity being seen here. So if we have to write the angular momentum of m2, that will be equal to lm2 is equal to, okay, now we should write p1 into r1. So we have p2 into r2. What is p2? P2 is m1. So p2 is m2 into v2, m2 into v2 into r2, right? Okay. Similarly, okay, let me draw one more diagram for the clarity. So say this is the third mass here, right? Third mass, m3. Now, where is m3 located at? m3 is at a distance. m3 is at a distance of m3 distance r3, right? m3 is a distance r3. And what is the velocity it is experiencing? This will experience a velocity v3, which would be r3 into omega towards that direction, right? So we will write the mathematical form. So we angular momentum of m3 is equal to linear momentum of 3 p3 into distance r3, which is equal to m3 v3 into r3. See, one thing that I can assure you is this question shouldn't be asked from a chapter, the laws of motion, because it's purely a concept related to circular motion. But the reason why I'm detailing here it maybe you'll understand better when we come to the discussion of rotation motion if we have a preliminary understanding about the topic. Okay, so now let us add these equations. So let me write lmn is equal. What would be lmn? Lmn would be equal to pn into rn, which is equal to mn vn into rn. Okay, now we'll add all these equations. What do you get? So when we add this equation, we'll add the LHS separately, which is L of m1 plus L of m2 plus L of m3 plus etc. up to L of mn is equal to m1 v1 r1 plus m2 v2 r2 plus m3 v3 r3 plus etc. up to mn vn rn. Now, what is lm1 plus lm2 plus lm3? We have it here. So lm1 plus lm2 plus lm3 etc. up to n terms is actually lnet, which is the total angular momentum. So we have this is total angular momentum. Lnet is equal to m1 v1 r1 plus m2 v2 r2 up to n terms, right? Okay. Now, I'm going to make a small rearrangement here. And how will I do that? I write like this: m1 r1 v1 plus m2 r2 v2 plus m3 r3 v3 plus etc. up to mn rn and then vn. Okay, and why are we doing this? We'll come to it. Now let us try to. Some of you might be wondering why did I write r omega and why did I not use it so far? Let's bring that concept now. So what is v1 is equal to r omega? What is v2 is equal to r2 omega? What is v3 is equal to r3 omega? Now we'll write those values here. So this will be equal to m1 into r1 into what is v1? V1 is r1 into omega plus m2 into r2 into what is v2? From here v2 is r2 into omega plus m3 into r3 into what is v3? V3 is r3 into omega plus etc. up to mn rn. What will be vn? Vn would be rn into omega. Okay, now look at the beauty of adding these equations. So what we get is m1 into r1 would be now be r1 square would be r1 square into omega, right, plus m2 into r2 would be r2 square into omega plus m3 into, right, r3 square into omega plus up to n terms we have mn into rn square into omega, right? Now what is common in all these terms? What is common in all the terms? Right, we have omega, which is common in all these terms. So let me highlight that part also. So omega here, omega is common to all terms, which means we can pull out omega out of these terms, right? So if I pull out omega out of these terms, what do we have in the rest terms? What we have is m1 r1 square plus m2 r2 square plus m3 r3 square, etc. up to mn rn square. Now this would further be equal to, well, let's say Lnet LHS is equal to RHS, which is sigma of m into r square times omega, right? Why? Because m1 r1 plus m2 r2 plus m3 r3. Okay, let me write down that also. So say we have m1 r1 plus m2 r2 is equal to sigma mr, right? So m1 r1 square plus m2 r2 square would be equal to sigma mr square. Simple logic. Okay, so that's how we get it. So that's how we get sigma mr square. Now what is Lnet? I abbreviate that as L is equal to, what is sigma mr square? See, this is where I say this question is not asked from laws of motion. This is purely based on the angular, circular motion. Now what is sigma mr square? We know that is moment of inertia I. So we have L is equal to I omega, right? So L is equal to I omega. So we have three formulas for angular momentum, linear momentum. One is linear momentum, which is m into v. Other is L is equal to m into v into r. Second one, and the third is L is equal to I omega. Okay, so these are three different formulas related to momentum. Okay, now let us come back to the question here. So what did we say in the discussion so far? We said that linear momentum P is equal to mv, and then we said that angular momentum about a point object, right? Angular momentum about a point object is L is equal to mv into r, and then we said for a rigid body, angular momentum L is equal to I into omega, and we will make use of the formula. P is equal to me. Sorry, L is equal to me into r. Now let us go to the question here. The angular momentum about the origin is conserved. So let us write like this: angular momentum is conserved, right? Angular momentum is conserved. Now see, when we say angular momentum is conserved, this actually means that the net external force, the net external torque acting on the body is equal to 0. This is what this means. Okay, net external torque acting on the body is 0. I'm not going to take you to the concept there. Let us first understand the mathematical part of this. So the angular momentum is conserved, right? So when we say angular momentum is conserved, this otherwise means that angular momentum initial should be equal to angular momentum final. Right, angular momentum initial should be equal to angular momentum final, or otherwise this can be said that angular momentum initial minus angular momentum final is equal to 0, right? Or we can say that change in angular momentum, which is initial minus final, is equal to 0. So we can say that delta L is equal to 0. Now what does delta L is equal to 0 implies? This implies that angular momentum L is actually a constant, right? Okay, now coming to the vector notation. This is where most people make a mistake, and we'll discuss more on this when we come to rotational motion. How did the cross product come into picture? Not now. Now, what is vector L? Vector L is r cross linear momentum, which is P. Okay, so I can write this as r cross. What is P? P is mass into velocity vector V. Okay. So if I write this further, I can write vector L is equal to r cross m cross V. Now, I'll write down this equation one more time. And then this time what I'll do is I'll differentiate both the equations with respect to time. Okay. I'll differentiate this equation with respect to time. In this case, what do we get? We get dl by dt is equal to vector r cross, sorry for that, vector r cross m into dv by dt, right? This further gives us that d by dt of L is equal to r cross m into what is dv by dt? It is the acceleration vector a, right? So we have dl by dt is equal to r cross what is ma? Ma is nothing but the vector force F, right? So we have dl by dt, is equal to r cross F. This is the formula what we'll use here. Now, since angular momentum is constant here, what is dl by dt? See, d by dt of a constant is actually equal to 0, right? So, okay, let me explain that since beginning. So d by dt of x square, sorry, d by dx of x square is 2x, but what is d by dx of 3? It is equal to 0. So the derivative of a constant is 0. Similarly, d by dt of k is equal to 0. Similarly, d by dt of L is also equal to 0. So we have r cross F is equal to, right? R cross F is equal to 0. Okay. So if we were to write this in a much correct way, so this derivative of the vector is equal to 0, right? So what we get here is actually a 0 vector. To be more precise, 0 vector. Now let us bring in the values here. Given in the question, what is given? We given that what is vector r? The vector r is given to us as 2i cap minus 6j cap minus 12k cap. What is vector f given to us? Vector f is given to us as, it's given to us as alpha I cap plus 3j cap plus 6k cap. Okay. Now, so r cross f is equal to 0 is what we get, right? So we have vector r cross vector f is equal to 0 vector, which is equal to 0 I cap plus 0 j cap plus 0 k cap, right? So if you take magnitude on both sides, okay, let us first do it the other way around and then I'll explain you the mathematical form as well. Now, what is vector r cross f? That we know it is equal to determinant ijk, right? Determinant ijk, 0i plus 0j plus 0k. R cross f means we'll first write the values of r here. 2 minus 6 minus 12, and f is alpha, 3 and 6. Okay, right. So from here we can expand the determinant. So write this as I. Okay, let us expand this directly. So I into determinant of minus 6 minus 12, 3 6 minus j into, right? So we have j is equal to 12 alpha 6 2, 12, alpha 6 plus k into, what do we have here? 2, 6, alpha 3. 2 minus 6, alpha 3. Sorry, I cap, j cap, k cap is equal to 0 I cap plus 0 j cap plus 0 k cap, right? So this would be I cap into 0 minus j cap into 6 and 2 is 12. So what we get is 12 minus 12 alpha plus k cap into, what we have here is 6 plus 6 alpha, right, is equal to 0 I cap plus 0 j cap plus 0 k cap. So if you write down the simplified form of vector, what we get is 0 I cap minus, wait, are we missing anything here? 12 minus, wait, I did a mistake. See, it's 6 into 2 is 12, minus into minus become plus, right? Plus 12 alpha. My bad. It's minus 12 here. Okay. So minus j into, we have is 12 plus 12 alpha into j cap plus, what we have is 6 plus 6 alpha into k cap is equal to 0 I cap plus 0 j cap plus 0 k cap, right? Okay. Now let us compare these two terms here. If we compare the j component alone, what do we get? What we get is minus of 12 plus 12 alpha is equal to 0, right? Okay, minus of 12 plus 12 alpha is equal to 0, which means 12 plus 12 alpha is equal to 0, which means 12 is equal to minus 12 alpha, and therefore we have alpha is equal to minus 1. Now let us compare the k components. What are the k components? K components says that 6 plus 6 alpha, right? So we have 6 plus 6 alpha is equal to, the k component is equal to 0. Therefore we have 6 is equal to minus 6 alpha, and again we have alpha is equal to minus 1.